guys, Mr. Ford here. In this video, it's going to be a continuation of our previous video that we did on circles on Unit 7. This is going to be lessons 8 and 10, and there's a lot of information to give in this actual video, so it'll just cover those two lessons, and there will be a lot that I review, go over again. So this video should be about the same length as the previous video, just going a little bit deeper. All right, so before we get this lesson started, there's a couple of things that we need to go over and just remind ourselves of, right? So we're dealing with circles. And at this point, all we've done with the circles is we've talked about um, first, we talked about radians, like a radius. We talked about a diameter, which is a chord that goes through a center. So we talked about chords. We talked about uh, central angles. We talked about arc lengths. We talked about inscribed angles. We talked about the relationship between the angle measures and those type of angles. And we're doing all this, but we have not mentioned yet um, those fundamental things that we learned a lot earlier in our education, a lot earlier in mathematics, when it comes to circles, and that is the perimeter or circumference of a circle and the area of a circle, right? So let's review those real quick. So the circumference of a circle, remember that's basically the same thing as the perimeter. That's going to equal 2 pi times radius, 2 pi r. Or we could say it's pi times diameter because the diameter is the same thing as 2 times the radius, right? So that's the circumference of a circle. And if you think about what an arc length is, a full arc length completely around a circle would be 360 degrees, right? That would equal 2 pi r. Okay, so just keep that in mind. We're not going to be dealing with that just yet, but keep that in mind. That is something to consider here in the future. I don't know what it did that. All right, the next thing, the area of a circle. Area of a circle. That's going to be pi times radius squared, right? Pi times our radius squared. So if you think about that in terms of the entire area of a circle, there's also going to be a relationship between the arc length or the angle measure, the central angle or inscribed angle, and the area of that circle. So just keep these things in mind when we're working on this lesson, okay? Because in this lesson, we're going to be dealing with arcs and sectors. And I think you're going to enjoy this one. I think this is going to be very helpful and it's going to benefit you a lot, especially when it comes time for the LEAP test. Just remember those two things, circumference of a circle and area of a circle. All right, so math talk, fractions of a circle. Evaluate each problem mentally. Well, I don't like having students evaluate something mentally because I can't see what they're doing. So instead, we're going to work these together. All right, so the first one, find the area of the shaded portion of the circle. All right, so let me zoom in on this first one. So we're finding the area of the shaded portion of the circle. So it's kind of plain to see that half of the circle is shaded, right? Because you know this because the line that separates the shaded and unshaded regions is a diameter, right? So let me just write that. That's a diameter. And if you recall, a diameter is nothing more than a chord that goes through the center, right? Now, let's talk about a few other things too. We could easily just find the area of the shaded portion. We could find the area of the entire circle and divide by 2. Let's do that before we move on, and I want to see if you can make that connection. So the area of a circle equals pi times radius squared, right? Well, our radius is 8. So the area of this one would be pi times 8 squared, right? And then 8 squared is 64, so 64 pi. And I'm just going to leave it in terms of pi, but that's the entire circle. So then we would have to, for the shaded region, so the area of the shaded region would be 64 pi divided by 2. So this one would be 32 pi, right? So this shaded region is 32 pi. And I'm going to keep it in terms of pi just because it's more precise that way for one, but it's easier to deal with, right? Okay, let's talk about some of the things we discussed in the last video. What you may not see, even though it kind of looks like a Pokemon ball or something, but what you may fail to recognize right away is you have an angle right here. That angle is 180 degrees, right? Because that angle is a straight line. You also would have an arc length associated with that angle, right? Now it's not highlighted on the circle, but you can see where I'm going with this. With a central angle of 180, if the central angle is 180, because that's a central angle, it goes through the center, right? It just happens to be a straight line. With a central angle of 180, then you would have an arc length of 180, right? Now, how do we refer to this shaded region? Well, this shaded region is what we call a sector, right? So the sector of that shaded region is 1/2. There's a formula or a way to find the area of a sector, right? So the area of a sector is going to equal any given angle theta over 360 times pi radius squared. So think about that. This angle, we call in this angle theta, right? So let me just put that. So angle theta is equal to 180 degrees. The overall circle, the whole circle, is 360. So if the shaded region was 360, this would be simple. It would be area equals 360 over 360 times pi radius squared, right? And then you would have 1 times pi radius squared, so it would just simply be pi radius squared. But since it's not the whole thing is shaded, let me go ahead and erase that and let's write what it is. So this would be 180 over 360 times pi, and I'm just going to take off the radius squared and actually put the radius of 8 squared, right? So the area of that shaded region is equal to 180 over 360 pi times 8 squared, right? So 180 over 360, that can reduce to 1/2. So then it would be 1/2 times pi times 8 squared. And of course, 8 squared would be 64, so it would be 64 pi over 2, which is just 32 pi. So we do the same thing. And nothing changes. I just want to show you a different way of doing it. Because think about this. If we just so happen to look at this circle as being half shaded. But what if it wasn't half shaded? Then what would you do? What if it wasn't a nice round number, or a number that turned into a nice, uh, easy to work with fraction? You got to have a way to solve it. You got to have a way to find it, and that's with this here. So the area of a sector is going to be, and don't forget that angle theta, right? So that's not a circle or a zero, that's just the Greek letter theta, right? Theta over 360 times pi radius squared. Now, the length of the highlighted portion, or the circle's circumference, the arc length, we know, we sort of just worked with that, but let's go over what this is. So this is an angle of 180, right? It's a straight angle. This circle has a radius of 8. So the circumference, if you recall, is going to be 2 pi r. 2 times pi times the radius. So the radius is 8. So the circumference would be 2 times pi times 8. Of course, 8 times 2 is 16, so 16 pi. But remember, this would be the circumference of the entire circle, right? So once again, we're in a position where we need to find, well, in this case, it just so happens to be half, but let's set ourselves up for success. What if we didn't know it was half? What if we just had a portion with a arc length? Then, once again, we could use our arc length. And this one, of course, we know is 180 over 360 times 2 pi r, right? So our circumference of that arc length is going to be 180 over 360 times 2 pi r. Okay, so that would be 1/2 times 2 pi, and then our radius is 8, right? So then I'm going to go ahead and multiply what's in parentheses, the 2 and the 8. So it'll be 1/2 of 16 pi, and then that would be 16 pi over 2, which simplifies to 8 pi. So the circumference of the entire circle was 16 pi, but just the distance, or the arc length of that sector, that highlighted area, would be 8 pi. So this will work with any sector length. All you have to do is put it over 100, put it over 360. All right, let's look at the next one. So for this one, if you notice, there's no length given. It appears to be about a fourth, but you can see this one important key illustration here. That means it's a 90-degree angle, right? So my arc length would also be 90 degrees, but I'm not going to find that just yet, because right now we're trying to find the shaded region, shaded portion of the circle, so that sector. So let's use our formula. Area of that shaded region would be 90 over 360 times pi radius squared, right? So then that would be 90 over 360 times pi times 6 squared, right? Now, 90 over 360, you may have guessed it at this point, would reduce to 1 over 4 times pi, and then 6 squared is 36. So let me just rewrite that as 1/4 times 36 pi, and that would be 36 pi over 4, which would end up being 9. Oops, 9 pi, right? So the area of that sector would be 9 pi because the area of the entire circle would be 36 pi, and this is really just a fourth of that overall area. So this was a nice round number also. This was 90 degrees. But what if it were like 82 degrees or 71 degrees, right? Those are going to be harder to deal with while just looking at and coming up with a fraction. Okay, so you need a way to do that. And that's going to be this formula that I gave you. So find the length of the highlighted portion of the circle's circumference. Of course, this one, once again, we would say 90 over 360 times 2 pi r, right? And then that's 90 over 360 times 2 pi times 6. And that would be, I'm going to simplify that 90 over 360 to 1/4 times 6 times 2 is 12 pi. So then that would be 12 pi over 4, which simplifies to 3 pi. So the circumference or the length of this arc length in terms of pi would be 3 pi, right? That if the entire circle, we were trying to find the circumference of the entire circle, of course it would be 4 times that amount, so that would be 12 pi, okay? But we were only looking for that sector. All right, so that's going to be one of the biggest challenges you'll face on your LEAP test. They love giving sector problems with area and sector length, so it's definitely something to be cognizant of and to make sure you know how to solve. So we'll look at these. I'm going to use these same methods instead. So first we're finding the so for each circle, find the area of the shaded sector and the length of the arc that outlines the sector. So we're finding the area and the circumference of those sectors, right? So first things first, I'm just going to look at these and I'm going to write. So this is 270 over 360 times pi radius squared. This one would be 60 over 360 times pi radius squared. And then this last one would be 135 over 360 pi radius squared. So those are going to be the area of each, right? So the area of each sector. And then the circumference is going to be the same. It would be 270 over 360 times 2 pi, or this one would be 60 over 360 times 2 pi, or, and then the last one would be 135 over 360 times 2 pi, or. All right, So we have limit space there at the bottom. I'd rather work them on the bottom so that way we don't take up too much space and you can still see it. So the first one, area is 270 over 360 times pi, and our radius is 10 squared, right? So 270 over 360. I know this can simplify. They both have a factor of 90, so that becomes 3 over 4 times pi. All right, then we have our radius squared, so 10 squared. Well, 10 squared is just going to be 100. So this would be 3/4 times 100 pi. So then that would be 300 pi over 4, which simplifies to 75 pi. So the area of that sector, the first one, would be 75 pi. Let's look at the circumference. Once again, 270 over 360, oops, times 2 pi or, and I'm just going to go ahead and write our or is 10. We know that's what the radius is. So here we go again. We got 3 over 4. It simplifies. And then 2 times 10 is going to be 20 pi, right? So then that would be 3 times 20 is 60 pi over 4, which simplifies to 15 pi. So the circumference or the length of that sector is going to be 15 pi. Now, I'm going to show you another way that we write that. Instead of using the C, instead of using this C, we'll often use an L for the length of that sector. So we'll say that sector length is 15 pi. All right, let's look at the next one. The next one still simplifies. It's not too bad because 60 over 60 over 360, and that would simplify, and I'll do that in the next step, times pi times radius squared, right? So then 60 over 360 times pi, and our radius is 12, so times 12 squared, right? 60 over 360 is going to simplify because 60 is a factor of 360. This becomes 1/6. 12 squared is going to be 144 pi, right? So then, and I know I work so fast sometimes I just forget to put my equal signs. So that would be 144 pi over 6, which is going to simplify to 24 pi, right? So that's the area. And remember, we always put, when we identify area, we always put it in units squared. So in these, all units are centimeters, so we would say centimeters squared, right? And I apologize, I forgot to do that in the first one. That would also be centimeters squared. So when we talk about area, we have to say units squared, right? So then the length is going to be 60 over 360 times 2 pi times 12, right? So length of, and I'm just going to change that to 1/6 again. 12 times 2 is 24 pi. So then length would be 24 pi over 6, which ends up being 4 pi. Oops. Okay. For the last one, let's do this. For the last one, we have area equals 135 over 360 times pi times our radius of 16 squared. Now, 135 over 360 is going to simplify also. It would take you a little bit of time to figure it out if you did the prime factorization of each one, or you simplified by numbers you know, like to start off with 5, then you would do 9, or you could do 5, then 3 again. But you would eventually see that they both have a factor of 45. So this would be A equals 3/8 times pi times 16 squared, right? So then 3/8, 16 squared is going to be 256. So 256 pi. So the next step would be, of course, multiplying 256 times 3 and then dividing by 8. But I know that 8 is a factor of 256. In fact, I'm going to write it up here. 8 goes into 256. 8 goes into 2 0 times, so 0 times 8 is 0. 2, bring down your 5. 8 goes into 25 3 times. 3 times 8 is 24. 1, bring down your 6. 8 goes into 16 2 times. 2 times 8 is 16. Remainder of 0, so that tells me that 8 goes into 256 32 times. So you could write each step and you could say, okay, 3 times 256 gives me 768 divided by 8, or you could simplify this 8 and this 256. That just becomes 32. So then you have 3 times 32 pi, which ends up being 96 pi. And then, of course, that would be in centimeters squared. Now, let's say you didn't know that that was something you could simplify. You would have had to multiply. I'm going to just go right here. You would have multiplied 3 times 256, and you would have got 768 pi over 8. Then you would have had to divide 768 by 8, and you would have ended up with the same thing, 96 pi centimeters squared. So all I did was kind of save a step just because I could see that it would be something that would be easier to do. All right, so for the last one, we'll do the length. Length, of course, is going to be the same thing, and I'm just going to use this smaller fraction that I've already figured out. So 3/8 times 2 pi times 16, right? Once again, 3/8, and then this is 2 times 16 is going to be 32 pi. So then you could go ahead and simplify here, or you can multiply it out. I'll just go ahead and multiply it out. 3 times 32 is 96 pi over 8, and then that would simplify to 12 pi, because 8 into 96, right? So 8 goes into 96 one time, 2 times, right? So 8 goes into 96 12 times, so that ends up being 12 pi, right? So the length of that sector is 12 pi. All right, so that's pretty challenging stuff, especially without a calculator. I'm just, I've been doing math for so long that these numbers are easier for me to deal with. But if you haven't been, you would probably want to use a calculator. All right, so I want to go over this and then I'm going to go ahead and move on to lesson 10. Uh, May says, I know how to find the area of a sector or the length of an arc for central angles like 180 degrees or 90 degrees, but I don't know how to do it for central angles that make up more complicated fractions of a circle. In this diagram, the sector's central angle measures theta degrees and the circle's radius uses R units. Use the diagram to tell me how to find the area of a sector and the length of the arc of any angle and radius measure. So those are the two things that we just did. I'm just showing you this, that it is part of the lesson, but I didn't like that the book makes you wait to find out. I'd rather get straight to it and show you so you have that knowledge. So, just a reminder, the area of a sector is going to equal angle theta, whatever that angle measure is for that central angle, over 360 times pi radius squared. The length of that sector area, or I'm sorry, of that arc is going to be theta over 360 times 2 pi times r. Those are the two things that you need to write down in your notes. That's what you need to know. You can do some mental math like I did with some of those, but there may come a time that you cannot do the mental math, right? So it may be a challenge. All right, so we'll do number 2 and then I'll move on to lesson 10. So this image shows a circle with the radius and central angle measurements. Find the area of the shaded sector and the length of the arc defined by the sector. So here we go. We're going to say area is, so it'd be 160 over 360 times pi times our radius is 5 squared, right? So that would be, now 160 over 360. I know that they're both divisible by 40 because 16 and 36 are both divisible by 4. So this would end up being 4 over 9 times 5 squared is 25 pi, right? Now, area equals 25 times 4 is 100 pi over 9. And there's no way to simplify this without using a decimal. So we're going to leave it as that. And let's see, it doesn't give us what the unit is. So I'm just going to say units squared. So the area of that sector, oh, it does say inches. I apologize. It's in the actual image. So that would be inches squared. So then the length of the sector, or the arc that defines the sector, would be 160 over 360 times 2 pi times our radius of 5, right? So once again, 160 over 360 is going to reduce to 4 over 9 times 2 times 5 is 10 pi, right? So then that would be 40 pi over 9. And that's not going to simplify either, so I'm just going to leave it at that, as the length is 40 pi over 9. All right, so lesson summary. This is wrapping up this lesson. A sector of a circle is the region enclosed by two radii. To find the area of a sector, start by calculating the area of the whole circle, dividing the measure of the central angle of the sector by 360 to find the fraction of the circle represented by the sector. Then multiply this fraction by the circle's total area. We can use a similar process to find the length of the arc lying on the boundary of this sector. I showed you guys how to do it. They make it a little more complicated than it really is, but sometimes that's the way it goes with these workbooks. All right, let's move on to lesson 10. Okay, so for lesson 10, I'm going to do things a little bit different. I'm going to go back to what I did in the previous video, which is I'm going to go over the lesson summary first. This one, it's kind of, all right, for lesson 10, I'm going to go over it a little bit differently than I did in the previous lesson 9. I'm going to pretty much go back to what I did in the previous video, which is I'm going to go over the lesson summary first. All right, so for lesson 10 summary, if we have the same central angle in two different circles, the length of the arc defined by the angle depends on the size of the circle. So we can use the relationship between the arc length and the circle's radius to get some information about the size of the central angle. For example, suppose circle A has a radius of 9 units and a central angle that defines an arc with a length of 3 pi. Circle B has a radius of 15 units and a central angle that defines an arc length of 5 pi. How do the two angles compare? So what we're dealing with here in this lesson is going to be dilations in circles, and not just the circles themselves, but their sector areas and arc lengths, right? Now, one thing I want you to remember, and we talked about this previously, it's definitely something that's important to note, and that is all circles, okay? All circles are similar. What does it mean to be similar? Remember, with similarity, same shape, but not necessarily the same size. All circles are similar. All right. So looking at these two, we will get into it here in a minute. For example, the circle has a radius of 9 units. This circle has a radius of 9 units and it has an arc length of 3 pi. This circle has a radius of 15 units and has a arc length of 5 pi. So you could see that if you set up a ratio or an equation, 3 pi over 9 would equal 5 pi over 15, right? Because they're both divisible by 3 here, so this would be pi over 3, and then these are both divisible by 5, so that would be also pi over 3. And pi over 3 does equal pi over 3, so yes, they would be similar, and those would be proportionate. All right, so let's get on with the lesson, and then we'll come back to this because we will see where this is taking us. All right. Han and Tyler are each completing the same set of tasks on an online homework site. Han is using his smartphone and Tyler is using his tablet. Their progress is indicated by the circle bar shown in the image. The shaded arc represents the tasks that have been completed. When the full circumference of the circle is shaded, they will be finished with all the tasks. So at this point, it appears to me as though they both have the same amount of work completed. If you think of it as a clock, what if we did think of it as a clock? Let's see. Let's say this is 12 o'clock. Over here would be somewhere around 4 o'clock, right? So that looks like they've gone from 12 to 4, basically about 1/3 of the way, right? Because 4 over 12 would be 1/3. Well, let's look at this one. Here's our 12 o'clock. This one also appears to be close to 4 o'clock. So it would look like it would be 4 over 12, which would be 1/3, right? So it looks like they're both a third of the way through. Tyler says the arc length of my progress bar measures 4.75 centimeters. So Tyler's is 4.75. The arc on Han's progress bar measures 2.25 centimeters. So I've completed more tasks than Han has. Do you agree with Tyler? Well, Tyler's wrong. Tyler arc length on the amount he's completed is only longer because his circle is bigger. It's a zoomed in view or a larger scale version, right? So I do not agree with Tyler. Neither should you. What information would you need to make a complete accurate comparison between the two students' progress? Well, basically, you need to know, and I'm just going to draw some more lines here. Let's use red. You need to know where here's the center. You need to know what that length is, that radius. We need to know what that radius is. If I did the same thing here, here's the center. I need to know what this radius is, right? Because those radius lengths are going to determine which one is higher or which one has completed more work. You'll need that information to be able to do so. So 10.2, a dilated circle. The image shows two circles. The second circle is a dilation of the first circle using a scale factor of 3. All right. So we look at these two circles. I drew this line previously because I wanted to figure out if the length was actually 3. So what I did was, let me zoom in. I took that length and I created the radius. And then from there, I moved it over. I placed it on here once, and then I made a mark, moved it, placed it on here twice, then I made a mark, then I placed it on there, moved it again, and as you can see, it's 3 times the length, right? So that scale factor is correct. Now, I'll admit the first time I did this one, I didn't even notice that they had put a scale factor on the previous page. So I did that for nothing basically, but it checks out. So I'm okay with the fact that I did a little bit extra work. For each part of the dilated image, determine the factor by which it's changed when compared to the corresponding part of the original circle. So the area of the sector. All right, so if it's a scale factor of 3, let's assume that this is going to be 1, a radius of 1. This will be a radius of 3. All right, so we'll use those two. So we'll find the area, which is 90 over 360, right? Because remember, we know that because it's got the square right here. And we're only talking about the area of the region that's shaded, right? That sector. It's going to be 90 over 360 times pi times our radius of 1 squared, right? So then that would be 1/4. We did that already. And then 1 squared is just 1, so it'd be pi times 1, which is just going to be pi over 4, right? So that's our area, and then of course we'll say units squared. I always get myself in trouble because I never look to see if they tell us what the units are, but we know that it's units squared. So area would equal pi over 4 units squared. That's the first one. The second one, actually, let's find the length. We'll find the arc length first. So the length would be 90 over 360 times uh, 2 pi times our radius of 1, right? So then we know that that's going to reduce to 1/4 times 2 times 1 is just going to be 2 pi. So then that would be 2 pi over 4, which simplifies to pi over 2. So our length is equal to pi over 2 in the first one. All right? Now, let's look at the second one. The area is going to be, once again, it's still the same, 90 over 360 times pi times our radius squared. Well, I'm going to use 1/4 again times pi. Our radius squared, that's 3 squared, which is going to be 9 pi, right? So then it would be, area would be 9 over 4, or I'm sorry, 9 pi over 4. And then, of course, that's units squared. So that's the area. So look at the comparison here. Now, the length of the arc is going to be 90 over 360 again, times 2 pi times 3, right? Because our radius is 3. So once again, 1/4 times 2 times 3 is 6 pi. So then that would be 6 pi over 4, which I can also simplify to 3 pi over 2. Okay, so the length would be 3 pi over 2, and that is here. So now I want to compare the two. So the areas of the sectors of the smaller was pi over 4 units, but the second one was 9 pi over 4. So that's an increase of 9 times, right? So the area of that sector is 9 times the area of the first, which that makes sense because it's got a radius of 3 instead of 1, and then 3 squared is 9. So the area increases by ninefold, right? By a scale factor of 9. The central angle, however, stays the same. They're both 90 degrees. So the central angle stays the same. The angle does not change. The radius, obviously, that has a scale factor of 3, right? So it's 3 times bigger. And the arc length also, remember the original was pi over 2, and it went all the way to 3 pi over 2. So that's also a scale factor of 3 times. So it increased by a scale factor of 3. Now, the last question. Oh man, this is a good one. I'm going to zoom in so you can see it. Let's look at this question. The ratio of the circle's circumference to its diameter. The ratio of the circumference to its diameter. Let's talk and speak in general terms. What is a ratio? A to B, A to B, or A to B, right? That's how you write a ratio. I'm going to use this one here. So, a circle's circumference, 2 pi, or a circle's diameter, 2 or. Would you agree that this is the circumference to diameter? It's written as a ratio. Well, what would that be? 2 pi r over 2 r. Well, those 2's cancel out, those r's cancel out, and we're left with pi. Say what, Mr. Ford? Say what is, this is pi. Well, what's pi, Mr. Ford? Well, that's funny you should ask. Pi is the ratio of a circle's circumference to its diameter. I just tricked you into taking in some pi. I'm not going to do 10.3. I think we've had plenty of practice with those, and I don't want to go too much further. But I did want to go back to the lesson summary, and let's see what it says here. It went over the example, right? So for example, suppose a circle A has a radius of 9 units and a central angle that defines the arc length of 3 pi. Circle B has a radius of 15 units and a central angle that defines an arc width length of 5 pi. How do the two angles compare? Since those arc lengths and radius, the radii, are proportionate, then those angles have to be congruent. Think of it like triangles, right? When you have triangles that have corresponding sides that are proportionate, then that means you have angles that are congruent and they are similar. For the angle in circle A, I'm reading here, the ratio of the arc length to the radius is 3 pi over 9, which can be rewritten as pi over 3. For the angle in circle B, the arc length to the radius is 5 pi over 15, which can also be written as pi over 3. That seems to indicate that the angles are the same size. So how can you check? Well, circle A's circumference is 18 pi units. The area of length 3 pi is 1/6 of 18 pi. So the angle measurement must be 1/6 of 360, which happens to be 60 degrees. Circle B's circumference is 30 pi units. The arc length is 5 pi, and is 1/6 of 30 pi. So this angle must also measure 1/6 of 360 degrees, which is 60 degrees. So the two angles indeed are congruent. This is a whole lot of good information. This is what you're going to need, and you need to know how to recognize and work through for your LEAP test. As always, I love you guys, but I just want you to be happy, and I just want you to stay golden, my nuggets.